Thank you all for coming. A lot of you won't be familiar with our technology, so I like to, when I try to describe it, I have to go back into my background a little bit to show how it came about, because my background is a little unusual. I got my master's degree back about 1970 at Wayne State University in freshwater biology, so I started working in phosphate pollution in lakes and things like that. And then in 1972, I had a unique opportunity to go out to California. And what I did out there there's a picture of me. I'm up there scrubbing out a tank that we used to keep lobsters in out there, because I was the director of a project where we were domesticating the American lobster. And this was through the University of California at Davis, and they had this project out of the Marine Laboratory in Bodega Bay, north of San Francisco. And what I had to do, of course, I had thousands of lobsters of all different sizes, tiny little larvae up to big 8-10 pounders. And I had to keep them alive in their toilets, literally, because obviously they live in the water and they poop in the water where they're living. So one of the issues we had, of course, was with our wastewater treatment systems, we had to be perfect. They had to work, otherwise the animals are dead. So it's a little different than a septic tank failing in your backyard. And the nice thing was that the co-principal investigator on this project was Dr. George Chabanaglis, who was probably the world's expert on sanitary engineering. He wrote the book, Metcalf and Eddy uses for every wastewater treatment plant in the world. And so he was a very expert at it. So I was able to work with him, which was really a great opportunity. And I did that for about a year, and then I decided to go back, and I enrolled at Berkeley and got my Ph.D. in marine ecology. So I did freshwater first and then marine ecology second. But I stayed at the lab for about 20 years. I was a researcher there. And in 1979, when I got my degree, I got a grant that had a half-time salary. So I figured I might as well do something else for the other half-time. So what I did was I started a winery, so out on the Sonoma coast. And I had a friend of mine, we bought a piece of property and started a winery, and so I got involved in winemaking. I'd been making wine all my life, but there I was doing it professionally. And that's where I really, really learned about microbiology at the industrial scale, and learned about the process of fermentation. And I like to laugh nowadays. People ask me what I'm doing, and I said, well, I used to ferment grapes into wine. Now I ferment shit into clean water. So it's all came full circle is what it did. And part of that was in 1989, a group of people approached me to do some research on a bacterial culture they'd developed for bioremediation. The guy who had developed this was doing it for actual composting, so he was a composter that did fertilizer production. And he had developed this bacterial blend, and it helped his process, made it work very well. And his son discovered he had a little packet of the bacteria after he had activated it and used it, and he had tossed it on the driveway. And about a week later, he came and he picked it up, and when he picked it up, underneath it, all the asphalt was gone. So the bacteria had just consumed the asphalt right there at the top of the surface, and he was looking at it and going, well, that's pretty interesting. And this was right around the time of the Exxon Valdez spill, and so there was a lot of interest in the oil spill. And they wanted me to do some research on it. And so I said, hey, that's a pretty interesting problem. And what we did is we developed a method to compost these contaminated sites. And the way we did it, you could see we would use a front-loading tractor. We'd excavate the contaminated soil. It might be from a leaking underground tank, or we did work down in Mexico with Pemex out in these oil fields that had just oil everywhere. It was just a mess. And the way we would do it is we would stack these windrows. We'd use a front-loading bucket. We'd spray the bacteria in it. We'd spray the bacteria in the soil as it was dropping out. And then about every third or fourth bucket, we would put in cow manure. And that way then we would lay this pile out in kind of layers. And the bacteria, of course, are in the cow manure, and they're very, very aggressive and working like mad because that's great food for them. That way, if they're in the toxic soil, they could slowly encroach there. They're next to the toxic soil, but they're not totally in it. And over time, we would turn the soil about once a week, respray the bacteria in the soil, And the bacteria would get really aggressive. Those piles would be 150 to 160 degrees. And it took about 8 weeks for about 8 turns, and we would totally eliminate all the petroleum. It would just be gone, and we'd end up with beautiful topsoil. And so, you know, the process was really pretty interesting. But I was dealing with these dairymen because I had to get cattle manure. And a dairyman in Petaluma, California had had a problem in that he was being cited for ammonia releases in his creek next to his farm. And it turned out that he had he had the barn up at one area. He would scrape the manure into his upper pond. Then he'd try to keep the solids there. The liquid would go down to a lower pond. Then he would irrigate from that lower pond, and he had just been irrigating this one knoll on top of his property for years and never bothered to move his irrigation gun. And it had built this biomat on top of the soil because it's all slimy cow manure. And of course, it always stunk. Whenever he would irrigate, his neighbors would all call and complain. And so, he was not the world's best farmer, frankly. But what we did, he asked us, he said, he's facing literally being closed down for these ammonia releases. So he asked us if our bacteria might help him. Thought about it a little bit, and I said, well, we can give it a try. So what we did is we set up a little trough up near his upper pond, and we grew the bacteria. We would use nutrients and things like that. So we'd grow this bacterial inoculum, and we started inoculating the upper pond. And when we did this, after about a week, I'm looking at this pond, and I'm going, that looks an awful lot like one of my large fermentation vats of Pinot Noir fermenting actively, because suddenly it just came to life. And the bacteria were in there working so aggressively that there's just bubbles and everything was stirring and everything was moving. And we were pretty intrigued by it. The bacteria then moved down into the lower pond, and the same thing happened down there. It just sort of moved through it over a couple of days. It's almost like a wave going through this big pond. And the first thing he noticed when he started irrigating is he wasn't getting angry phone calls because it had eliminated the odor almost immediately. The other thing is, over time, of course, it started to clear that area that he'd been irrigating for so long. It ate through that biomat, and the percolation started working again. So when it rained, it didn't just run off into the creek, which is what his problem was before. And once we started seeing that, immediately we brought him back into to compliance really within that first month, and he was fine after that. But I was intrigued by it because I'm just watching all this activity, and he actually, what we saw was, normally that manure was just viscous. It's very slimy. It's just like in a septic tank. You got septic stuff. It's very slimy. And that was his problem in his farm. So he had a screen. He would try to screen out his fiber and his solids in his manure, but the minute he'd try to run something through it, would clog it up. And so he really never used it. Well, after a couple weeks of watching this fermentation going on, I noticed that the liquid lost that viscosity. So it was now just plain water. So he started running his stuff through his screen, and he got beautiful, clean fiber off of it. And in fact, it was so clean that he stopped using sand to bed his cows on, and instead used recovered manure fiber as the bedding for the cattle. And so saved him a lot of money. He liked it. And the cows actually did much better. So we were very intrigued by this whole thing. And it got me thinking about bacteria. Now, as a winemaker, one of the things as a winemaker I had learned is we always used bacteria or yeast strains that we could buy commercially. And we always picked the ones we want because there are thousands, well, there are millions and millions of different kinds of bacteria out there in the world. And so all the industries, if you look at winemaking or brewing or pharmaceuticals or bioremediation, all these industries that use microbes always use selected organisms, and then they inoculate the process. That's just the way they do it. They've been doing that ever since Louis Pasteur. Except the wastewater industry, largest microbiological industry on earth. And it's still literally pre-Louis Pasteur. Everybody expects the bacteria that come wandering into their system to be the ones that they want. Well, it never made sense to me as a biologist. I mean, when I wrote papers, I always had to tell the name of the species I was working on when I wrote my papers. But a sanitary engineer didn't have to even, you'd ask them, what bacteria are you using? And they give you a blank stare because they didn't know. So it got me thinking then I started thinking about the computer industry. I'm going, well, back when I was a student, a computer was all hardware. It was a giant building. Our computer in the University of Miami, where I got my bachelor's degree, was a 3-story building, which with giant adding machine is really what it was. But then about 1980, Steve Jobs, Bill Gates, some of these guys, they started thinking, you know what? We could make computation a lot more effective if we started working on the software. So they shifted their emphasis from the hardware part of it and they started working on the software. And that symbiosis, when they started doing that, allowed the technology to just, boom, explode. And now, your pocket, the thing sitting in your pocket, is a supercomputer. I mean, it's way beyond anything we had in there. In fact, it would be impossible. And it was really made, it was made because of the software. So I started thinking about wastewater. Well, if you look at a big municipal wastewater plant, it's the equivalent of the old-fashioned mainframe computer. It's all hardware. And it works, but it's not very efficient. Because you can build them like that for big cities, obviously, because they've got a tax base, they've got a fee base, they have plenty of money to throw around, or at least they did back in the 70s and 80s when they built these things. But again, why not start looking at the software? So I figured if we could do what the computer industry did by shifting our focus to the software, which is the bacteria, maybe we could do that same thing. We could get a burst of creativity in this whole process. So when you think about software, the bacterial software that we're talking about, you have to realize where it comes from, most of it. You look at a septic tank. All the bacteria coming into that septic tank are coming from feces. It's from human intestines. It's because it's all going right down in the toilet. Well, you got to think a little bit about those bacteria. Now, that's the dominant bacteria that's in a septic tank. So what are those bacteria like? How do they live? What are their characteristics? And are those characteristics any good for actual wastewater treatment? Well, for a number of reasons, they really aren't. In fact, they're probably the worst you could get. In the first place, the bacteria that live in your intestines cannot eat very much food. If they did, you'd starve. They're in your stomach. You're giving them that food. What they're doing is they're breaking down large molecules into small molecules that we can absorb across our intestines, which is great. I mean, it helps us. And if we need those bacteria, you wouldn't survive without them. But they're not going to do much in the septic tank. They just don't eat much. They can't. They quite literally cannot. They've evolved totally not to do that. The other thing is their temperature range. Ever since there have been warm-blooded animals on Earth, these bacteria have adapted to a temperature that's about 98.6 degrees that hardly ever changes. So their temperature not only is pretty high, no septic tanks, very few septic tanks are 98.6 degrees. And so they go in, they hit the toilet, they're in temperature shock. They go down in the septic tank. It's too cold. So they're really just not doing much at all. So when you think about what's going on in the septic tank, very little actual biological digestion occurs in there. Most of it is physical separation, solids settle, scum rises, there's a little bit of activity. But if you actually look in a septic tank, you will see occasional bubbles, but hardly any. And same like that with a manure pond. You look at them, there's a bubble here, a bubble there. When it's summertime, when it warms up, you get a little more bubbling. But again, that's just not much activity. You've got a huge amount of food sitting in there that's just going to waste. And the other thing then is that whole issue of mucus, this slimy characteristic that we were seeing in the dairy manure is caused by a compound called mucus. The bacteria that are living in your stomachs are being attacked by enzymes and acids all the time, so they protect themselves by secreting a really, really thick layer of mucus. And all bacteria will produce a certain amount of mucus, but the ones that live in your intestine produce a huge amount because they really need it. So they go in the septic tank, and that mucus is just sitting there. Now, it turns out that mucus is a sugar compound. And what I was seeing in the dairy manure pond was the bacteria that were going after that sugar, and they were fermenting it in the same way that the yeast in my winemaking would go in and ferment the sugar in that. And the reason they can do that is that sugar has oxygen in it. So they're in an anaerobic environment. This manure pond didn't have any air. There was no oxygen, but they were still very, very active. The bacteria need oxygen. They have to have oxygen. They're not anaerobic. But they can get it from the air, or they can get it from the sugar. And they get it through the process of fermentation. So that's how they work, and that's why it became so effective. But it is also the reason you get that. The base, when you look at any kind of leach system, eventually you get in there, you got this black biomat sitting underneath the trench, and of course it's from that mucus that's going out there. Because no matter how well that septic tank keeps the solids out of the field, the mucus is constantly going out there. It's this colloidal material, it's in suspension, so it just goes out to the field, and over time it simply coats everything, and it's just like putting mayonnaise on a Brillo pad, you know, you're not going to get any water through that. So that's the big problem. And right about that time, I was talking to a gentleman who had experience, he had a TerraLift machine, and he was doing work in the septic industry, and he was frustrated because he'd go out and he'd do a TerraLift and he would restore a failed leach field, get it going again, but it would only go for another year or so. It would just clog back up again. So he was trying to figure out what he could do. And we got talking about it, and I said, well, it's interesting. You know, I've got a culture of bacteria that we use for bioremediation that would be perfect for this. But how do I get it to survive in a septic tank? Again, these are aerobic bacteria. And the thing is, we buy them as spores. So you can go down to the hardware, you can buy, you know, any kind of bacterial blend you want. I can't even remember the one that everybody buys. So if you go out there and you buy those bacteria, you put them in a leach field or you put them in a septic tank, they're spores. They don't germinate. They can't germinate. It's just the wrong environment for them. They're aerobic bacteria. You get a temporary effect because when you buy commercial bacteria, you're also getting all the enzymes that the bacteria produced when they grew them. And they don't separate that out. It'd be too expensive to purify the bacteria. So you get the culture of bacteria, and it's got all these enzymes in it. Put that in there, the enzymes will work for a while. They'll liquefy stuff, but then they're gone. You know, they don't last very long because they're protein. They're going to get eaten. So it never made much sense. And I'm looking at it and I'm going, well, if we're going to be able to use these bacteria to try and recover failed leach fields, I've got to figure out how to get air into a septic tank and do it in a way that we can create sort of like a refuge that would be a place to grow the bacteria. So the bacteria that we were using, these are the culture that we were using actually, that I wanted to get into the tank, of course, came from the forest leaf litter zone. So these are the bacteria that live out in the forest leaves. So every year you've got all these leaves fall, and the bacteria, when they live out there, have several advantages. Number one, well, I won't get to that yet. The way they live, their lifestyle is that they're in the soil as a spore. The leaves fall in the wintertime and get covered with snow. The snow's, everything's cold, so nothing's happening. And then in the spring, it starts to warm up and everything melts, and the bacteria then germinate from their spores because they're getting ready. But the trick is they got to compete with each other. There's a whole bunch of bacteria out there, and the way you compete in evolution is you leave behind more babies, you know? And the way these guys do it is eat as much as you can, as fast as you can, and eat faster than your neighbor and produce more offspring, reproduce faster. And then when you run out of food, you just go back to spore. Wait till the next time. And so that's how organisms that live in these periodic or episodic environments, that's how they compete. They compete by just getting in there, eat fast, and then go, you know, have a resting stage for the next time. Which I looked at it and I said, well, you know, that's actually a nice characteristic if you want to treat wastewater. You want something that really has a good appetite. And of course, the other thing is they're living in their food. They're responsible for eating billions of tons of dead leaves every year. So they have to have a big appetite. And they're out in the outer environment. They can break down cellulose because they eat dead leaves. So toilet paper is no big deal for them. In fact, it's just candy. They were correct. Almost all aspects of their life history really worked. But one of the unique things, again, was they can survive in anaerobic conditions. If there's sugar available, they can grow with air. We put them in the tank, use air to grow them, but they can go out into a leach field where there's no oxygen, and because they have all this mucus sitting in the soil, which is just sugar, they can ferment it, and they get their oxygen in that process, and that way they stay alive when they're out in the leach field and they keep working at it. So they were almost ideal for what we wanted. But again, how do we get them going in that tank? That was the real challenge. And the way we looked at it, I had done a lot of work, of course, in the aquaculture trade. We made aquaria all the time, and I would do aeration systems for the aquaria trade, and I had a beautiful aquarium in our tasting room. And so I was familiar with the way we would use air to move water in aquaria. You know, a normal aquarium has a bottom that's sand and gravel and a little space underneath it. Then you stick a tube down through that into that lower space and put an air stone in there. It'll move the water up, and then the water will come through, and then the water in the tank will then slowly pass through the soil, through the bacteria living in the soil, and that's how an aquarium filter works. And I looked at that principle and I thought, well, how about I'll use the same principle, but what we'll do, since we were dealing with old septic tanks and old systems, we had no idea. We had to build something that would be small, that we could get into a septic tank, and that would work even if it was an old, fiberglass tank, or heck, I did redwood septic tanks out in California that worked perfectly. We never knew what we were going to come up with, what kind of tank it would be, how big it would be, how deep it would be. We said, okay, as long as we can have something that we can put in that tank and it can work all by itself, it doesn't matter. We can put it in any tank we can run into. And so that's how we designed it. And the way we did it was we took the column, so that's about 3 feet tall, a foot in diameter. At the base of it, we've got a fine bubble diffuser. So at the base of the column is a microfine bubble diffuser. We use a little air pump that sits over by the house, run air out through the air line, then goes down into the unit. And as the air is going through the diffuser, it's pushing water. So it's acting like a pump. And it's pushing water up through here because there are openings at the bottom. We have a little wrapping at the bottom that's sort of a rough filter to keep toilet paper and junk out of it. And the water goes in and circulates through. And with a little 40 watt or a 60 watt air pump, we can move about 20,000 gallons a day through this unit. So it's a very, very effective pump. It's pumping a huge amount of water. And what it's doing, of course, inside of it, you can see we have this same kind of cuspated plastic. That's inside the unit. And what that does is it acts as a fixed film surface for the bacteria to colonize. And the way we get the bacteria in there, we just put it in a little tea bag like this. The bacterial spores are blended with compost. And the reason we do that is this acts like a mother culture. Put it in here, the bacteria then germinate. They then circulate. They're circulating all through the tank. They're coating, they'll get on all the concrete and everything else attached to it because they like to be attached. Then they'll attach inside of it. So we've got this big colony of bacteria that's sitting in here, and we're bringing the food to it and bringing food and oxygen to the bacteria. And that way they can work at it, but we're doing it like in a 1,000 gallon septic tank. That entire content of that tank will go through here 20 times a day. So we're just constantly feeding the bacteria. They just get the food all the time. And the reason I liked doing it this way was, as that fine bubble comes up through that matrix, it's really more like a foam. So you're not just getting water that's dissolved in oxygen, oxygen dissolved in water. Water doesn't hold very much oxygen. You can only get about 8 milligrams per liter in water. But they're not really, the bacteria are sitting there on a surface, and these bubbles are coming through all the time, so they're being exposed to oxygen in the air, actually. So it's really, in fact, one of the things we said, let's create a soil-like environment inside this unit because we're dealing with soil bacteria. And we didn't know if we were successful until one day I was at a septic tank in California, and I pulled out the stick in here, and it was a redwood septic tank, and it was completely covered with earthworms. It was just packed with earthworms. There were earthworms, eggs all over it. And I'm looking at it, I'm going, well, God, we wanted a soil-like environment. Earthworms live in soil. You don't find them in septic tanks very often, you know? So we realized that we had succeeded. We were giving them enough air for the bacteria, and so we started putting those in. When we started doing this, of course, and again, we wanted something simple, easy to install, portable, and then scalable. Like if I have a big project, we work with Stuart, he does large projects where we put in multiple units. We can put in 20 of them. I did a system over in Tripoli, Libya, where we had 200 SludgeHammers in a 1.4 million gallon septic tank. So that was a big project, you know. So I wanted that to have that flexibility, and we did. The way we do it, of course, is simple. All you want, it just sits in the tank. Air out by the house. And it's just sitting there by its own weight. You don't, the little half-inch PVC is enough to hold it upright. When we first started out, we were putting them in the outlet chamber of the tanks because we were trying to get the bacteria out to the leach field. But I had a client whose tank had died because his mother was on chemotherapy. Field had failed, so we went out, put the SludgeHammer in, and I wasn't sure if we could deal with chemotherapy. But I realized that we had worked with some pretty toxic environments. We'd used these bacteria in some pretty nasty places down in Mexico with this oil and asphalt and things like that. So it was at least worth a try. But at that home, I said, no, I want to put it in the inlet chamber because I want to get at the chemotherapy agents as far upstream as possible, just to see if it would work. So we put it in the inlet chamber, and I was curious about it. I came back about a month later. The field was working, everything had recovered, and I looked in that inlet chamber, and I saw just clear water, you know? It was just bubbling like mad, no toilet paper, no solids, no fecal material, anything like that, and it's in the inlet chamber. And I was actually a little bit surprised. So I started probing around. I thought maybe it was settling faster because we were breaking down the viscosity. I probed around, and there was nothing in the tank. So that was when we realized, well, if we're going to be putting them in tanks, why not put them in the inlet chamber? Save a little, you know, save a little on pumping if you can. And it turns out we've had systems operating now in northern Michigan for up to 20 years now that have never been pumped. And a lot of people will look at that with a great deal of skepticism, and I always agree with them because I hate to say never, you know, it's one of those things. So people ask, will I ever have to pump again? I said, well, you might, but we've got an awful lot of them that nobody's ever pumped. I thought a bit about that, though, and it turns out actually we are pumping the tank. It's just that we're digesting the solid load in the tank to such a low level that it can, any of those solids that are remaining, they just go out with the flow into the field. They don't cause any problem in the field because the solids now are just bacteria. It's not toilet paper anymore. It's just bacteria, the slime is gone. So we can literally pump that tank every time we flush a toilet. We're pumping that septic tank. It's going out into the field. So it isn't that we aren't pumping tanks. It's just we're not using a truck to do it. So when we started doing this, we were in Sonoma County, in the county regulators. We went into the permit, you know, to the health department and said, you know, how do we get a permit to put these in? They said, well, you can't put them in. And we go, well, why not? And they said, it's not in our code. And I said, well, you know, if it's not in your code, that means we can put them in because it's not restricted in your code. And they go, no, it doesn't work that way. But we put a few in, we started putting them in, and eventually the county came down on us and said, no, sorry, you just can't do that. However, if you get an IAPMO approval, if you can get a standard through IAPMO and get an approval and an IAPMO certificate, we can permit them. So at the time when they were confronting us, we had already gotten into that process we were about 6 months into it. What we did was we set up a system at UC Davis at their wastewater plant where we put in 2 side-by-side septic tanks loading 3 leach units. These were just big, you know, things that we could saturate, use them as a little leach field. And we had to load them. So we had septic tank, the wastewater coming into the septic tanks, going out. We were loading them at about 10 gallons per square foot per day. So we were really overloading them as much as possible. And it took about 6 months to fail those. We were able to measure what percolated through, and then it had an overflow on the top. When we got to the point where only 1 gallon per minute was percolating through, we started our test. What the test consisted of is a SludgeHammer in one tank and a SludgeHammer in the other tank, both of them. One with bacteria and one without. And the reason we did it that way is it's already been known that you can use an ATU, an aerobic treatment unit, to recover a failed leach field. Part of the problem is that those are always regulated by NSF. So you have to have an NSF 40 system. NSF does not allow retrofitting. You have to put in a brand new system. So it was impractical to ever use aerobic treatment to try and recover these leach fields, just because the NSF has a monopoly on everything. And so we looked at it and said, well, if we can demonstrate that we can partially recover it just with air, but then put the one with bacteria next to it and show that it can recover it at least twice the rate, then that's what the standard says. So it's the standard created the name. They said, well, what do we call this thing? It's not an ATU. So IAPMO came up with the name aerobic bacterial generator. So it's really an ABG. When we put it in there, actually we recovered it at almost 3 times the rate with the bacteria. It made a huge difference in terms of the recovery rate. And we got certified by IAPMO, and we're now listed. We've been listed with IAPMO since 2003. And we're really the only product on the market in that category. So that helped us. It got, you know, at least they allowed us to put them in. That was one break. And as we started getting more, you know, a lot of experience with that, after we'd put in probably 100 of these systems, I kept looking at the tanks we'd put them in, and the tanks always had, well, you know, you'd pull a water sample out of it and it would look like that. We were always just getting clear water in the tanks. So I finally realized, well, it really is an ATU. It's not just an ABG. It is an ATU as well, because it does treat water. I mean, you get a really high quality effluent from it. So we might as well get an NSF 40. So we went ahead and we went to NSF, and we did. They have a test site up in British Columbia, so it was convenient for me. I was living in California. And we put in the unit, but I learned something about the NSF process and one of the flaws in the whole NSF concept. That is, in order for them to test, they have multiple technologies they're testing all at the same time. So they have to have exactly the same load going to each one of those units in order to be able to compare apples with apples. The way they did that is they'd have it's at a wastewater plant. They would take the material from the headworks load, run it through a commutator pump, and grind it really, really fine. It would come in then to a raceway. So they had this big raceway with the water, with pumps in it that were just constantly circulating the water round and round and round. And that way, any dose to a tank, whenever it was called for, was getting identical doses. The problem with that is the material was absolutely nothing like anything you would ever find in a septic tank or at a home. It's just completely, it was so artificial, it didn't make any sense. Well, traditionally, the way NSF models have dealt with that is they always have a trash tank as part of it. It's because up at the NSF site, there's no way you can possibly treat this stuff. It's all in suspension. So if you hold it in a septic tank in front of it, then you can treat the liquid part of it that's left over. So that's the whole design for NSF systems. Well, our system, we put them in the inlet chamber because we wanted to digest those solids. But the problem there, I tried it at NSF, but the problem is that the material was so fine, it would just pass through. And so the way I dealt with it was we came up with these materials that were floating. I went and got it's like filter for a furnace filter material, and we got it in bulk, and it was about inch thick. It looked like a giant Brillo pad, really, is what it was. And we came up with several different amendments. So I had a little unit that's like a donut that fits over the top. Then I set a couple that were just sheets that were floating, and then we put one great big one that went all the way across the tank at the end of it there, like a curtain. And as soon as I put those in, it worked like a charm, because all those solids got suspended. They got captured, and because they were in the air, they got digested. We didn't really get any buildup at all on that fabric, and it worked for a long time. And it pointed out one of the cautions about using NSF ATUs is that they're designing for a 6-month test. So they build a trash tank that holds 6 months worth of load. Then they treat the soluble, so it means they can't be very powerful because they only have to deal with the soluble waste anyhow, which is only about half the load. So they got these systems that work great at an NSF facility for 6 months. You put it in the field, if you don't pump that tank every 6 months, you got some serious problems. They're just not designed to handle solids, and most of them are designed to hold 6 months worth of solids. So that's one of the real things you have to watch out for with most ATUs. But as we were doing it, of course, now we're, as we became an ATU, we started thinking about it. I was living in California at the time, and I'm from Michigan originally, and I missed lawns. I didn't see lawns anywhere, we just couldn't have lawns. We didn't have enough water. My well, you talk about a lot of water here, our well was about 1/4 to 1/2 gallon per minute. So we didn't have a lot of water. I had to have a big 3,000 gallon storage tank. And so everything we did was drip. But I had rented our house out to a couple that had 5 kids. And about 5 years later, I get a phone call that they had failed my leach field. And I'm going, oh my God, they failed my leach field. It was sewage backing up downstairs. I said, well, thank God, at least I got that. So I went over, put the SludgeHammer in, recovered our leach field. And then a year later, my wife and I moved back to the house. And finally I said, darn it, I really do want a lawn. Now we've got this tank. I got all this beautiful water in here. It's got nitrogen, it's got phosphorus, it's got all this fertilizer value. Why aren't we using it? So what we did is she and I went down, we cleared an area right by our pool, built a retaining wall. I, jackhammered our old cement patio and got these big blocks, and my wife went over there and built this wall. We filled in the area with wheelbarrows, put geoflow drip tubing, and we laid the drip tubing on that, and then just brought in topsoil and then put sod on, and I ended up with probably the only green lawn in Sonoma County. And I really liked that. And at the time, I had started out, I was working with our partner here in Michigan, and he was telling me about projects he was doing up in Petoskey using same thing, subsurface drip. And I'm going, huh? It gets 20 below zero up there. What are you talking about? How could you possibly use subsurface drip up in Petoskey, Michigan? Then he told me about a project we had done over at University of Minnesota, where we were working with creamery waste, and they used subsurface drip there too. And I'm just, I had a hard time believing that he was, was legitimate. But he said, no, it's really easy. Your line goes out, when you send your line out to supply it, then you have drip tubings going across, that's a manifold, and then you have a return line that's coming back to your pump tank. You turn it on, the water's passing through the whole system, coming back to the pump tank. You then use valves to adjust your pressure in the field to determine your drip rate. But it means when the pump shuts off after the dose, everything drains back, so there's nothing in the field to freeze. And I thought, well, sounds novel. So we put in several systems. And over time, we discovered, and we've now had them in for 15 years up there, we have never had a freezing problem with a drip system, and they're only 8 inches deep, And it all was in that engineering, how you lay them out. And since we discovered that, what we discovered also is that drip is, I just think it's wonderful technology myself. Again, I'm an ecologist. I had done a lot of work on wastewater trying to grow trees. We were trying to grow redwood trees in California with wastewater. And I'm thinking, wow, why isn't wastewater being used productively everywhere? How come, especially septic tanks? You send liquid out to a leach bed or a leach trench, that water is going down and it's 2 or 3 feet deep where it enters the soil. There's nothing down there. That's a desert. It's just dirt. There's hardly any biology below about 1 foot. And anybody who works in a garden, you dig your soil, that upper foot's beautiful. It's got all this humic material, it's got insects, it's got worms, it's got protozoans, it's got all kinds of stuff in there. Well, all of that is working to purify that waste, but none of it's being used in the traditional industry. It's all going in way down below where nothing happens to it. You get a little bit of, you'll get good digestion of that, but you're not getting any real productive use from it. And of course, the other thing is, because my original work at Wayne State was on phosphate pollution in lakes, I was concerned about phosphate getting into lakes. Same thing with nitrogen. You got all these issues. Well, we started thinking about drip, and when you put in a drip system, we've got it to the point where it's easier for us to do a drip system than any other disposal field. It goes in like a charm, simple to do. My wife and I did it with wheelbarrows, it's that simple. So I recommend it for almost all these things, but what we found was when you put that water in at about 6 to 8 inches you're in that root zone. So the plants have direct uptake of the nutrients. And the way it works, and this is why it's so valuable, is the concentration of nutrients is very low. You know, you look at fertilizer that you put on your lawn, that's measured in percentage. You got 10, 10, 30 or something like that. Well, that's 10% phosphate. That's 100,000 parts per million, 100,000 milligrams per liter. You've got 5 milligrams per liter of phosphate in your wastewater. It's infinitesimal when you compare it to what you're putting on your lawn here. Well, no wonder all that stuff runs off into the lake. It's so concentrated that hardly any of it gets taken up by the plants. However, if you're putting it in there, which each drop that you're putting in there has the fertilizer in it, the plant's taking that drop, it's taking all that fertilizer, it's getting all the fertilizer it needs because it's getting it constantly, but it's getting it at an extremely low dose, and it uses it all. So it means none of it gets wasted. And to me, as an ecologist, that's what I want. I want ecosystems that work. I want to see ecosystems that really flourish. So that's part of the reason we really have pushed this. The other thing is that because we deal with, we're up in where we are in Petoskey, there's lakes everywhere. And we have the biggest one of all. We got Lake Michigan sitting there, you know, and we've got a lot of systems on the shore of Lake Michigan. And we did a lot of research. We had a project at a condominium complex with 120 residences that had 9 cluster systems. So they were doing, each system was about 6,000 gallons a day. So their total load was 50 to 60,000 gallons per day in this community. And their septic tanks had contaminated their groundwater underneath. There was nitrate in their groundwater monitoring wells. So we were working, so they had to renew their permit, and Eagle, our new Department of Health in the state of Michigan, they wanted them to do nitrogen reduction because of the nitrate contamination. So I had seen in California that our system, because we were changing the bacteriology in our system so drastically, we totally changed the nitrogen dynamics. And we ended up with, almost by accident, we ended up creating this situation where we get an aerobic form of denitrification that occurs in the tank or in the soil. I found it first in the soil we had a project at the city of Santa Rosa. We had a mound that had failed. And so we took samples from the septic tank. We had nothing but ammonia. It was all ammonia in the septic tank, which surprised me in the first place because typically an aerobic system will convert ammonia to nitrate. But this wasn't the case. Everything was staying as ammonia. Then went out into the mound, and in the tank, the ammonia was like 86 milligrams per liter. It was really quite high. And I was expecting to see it disappear in the mound, but all get converted to nitrate, which is typically what happens. Most mounds or leach fields, that ammonia gets transferred into nitrate. When we did the samples, the city of Santa Rosa sampled for us, the ammonia had dropped from 86 down to less than 1. It was 0.9 of ammonia. So the ammonia had gotten all oxidized, but we didn't have any nitrate. And I was really confused because we should have had nitrate. By any engineering standard, and any biologist would have told you, no, you're going to have nitrate. But we didn't. And I finally discovered that when I looked into it, is the way nitrogen is normally done, you aerate without bacteria. If you just put it in a tank and aerate waste, you'd aerate it long enough, there was a bacteria that comes in that oxidizes ammonia from NH3 to NO2, which is called nitrite. It's not nitrate. Once you've got the NO2, another bacteria comes in that's called Nitrobacter. It then takes the NO2 and converts it to NO3. Now, once you've got NO3, it's very stable. It's hard to get rid of. But that transition stage, that NO2 in the process, well, in most systems, you never see it because the two bacteria pair up. So they're actually side by side, and they have to be fixed. They have to be on a surface. And when they're on that surface, they're side by side. So when nitrosomonas converts ammonia to NO2, Nitrobacter takes NO2 to NO3 almost instantaneously. So you never find it in a tank. So nobody in the industry has any experience working with NO2. They hardly ever see it. Well, what we discovered is our bacteria like that NO2 also. Nitrobacter is going to take the NO2 and make NO3, but our bacteria will go, no, we'll take the oxygen off of that and we'll make it into nitrogen gas. So they short circuit the whole thing. So if we can get our systems and part of the problem is it's hard to get the ammonia oxidizing bacteria to go in our systems in the first place because our bacteria are pretty aggressive. But what we find up in the soil, when it gets into the soil, they're already there. Those bacteria, the nitrogen bacteria, are already in the soil. So if I send out the ammonia from our tank along with our bacteria, we short circuit that whole thing and all the nitrogen just goes off as nitrogen gas. So we get almost instantaneous denitrification. Well, that's helpful when you're in an area where you're worried about polluting lakes. And so we had to prove that to Department of Health up in Michigan. So we did a series of studies in these leach fields where we put lysimeters that are little tubes with a ceramic end. You bury it, you can do them at different depths. And then you pull a vacuum on that and it'll pull a groundwater sample in so we could get groundwater samples. And what we did is we proved the fact that we were eliminating the nitrate. And then so we put the system in and it worked like a charm. It's been up there for 15 years now. It's working great. So now we do that, everywhere we look. It'll spontaneously happen in our tanks now in the septic tank, but it usually takes about a year. It doesn't happen instantaneously. But after about a year, our tanks usually have almost no nitrogen in them. They still have the phosphorus and they still have enough nitrogen. It's only maybe 5 to 10 milligrams per liter. But again, as a fertilizer, that's plenty. The plants have as much as they want. It just means none of it is passing through and going down in the groundwater, which is a benefit. Then around lakes, what's nice about it is if you're putting your leach field, the point of disposal, 10 inches under the surface, that means you gained a couple extra feet of distance from groundwater. So we have all these properties around lakes in Michigan that have groundwater issues, because they're right next to a lake. Naturally, they're going to have high groundwater. But by just that simple fact that we're dispersing it higher, we've made all kinds of properties usable that weren't usable before. And the other thing it does is it eliminates the need for these giant mounds. We can make a mound with our system if we have to, but it's a nice gentle mound and it really just looks like a piece of lawn. It doesn't look like a mound at all. So it's very advantageous for that. But we had one system where the homeowner had a mound, but it was not a wastewater mound. It was a landscaping mound out in front of his yard. He had a failing system, so he had to do something. He was going to have to he had a piece of property across the road. He was going to have to go under the road, cut down a whole forest, put in a system, a big mound over there. But we looked at it, and as I was walking on his property, I was looking at this gorgeous landscape mound. He had all this beautiful vegetation all through there. And I talked to the regulator, and I said, he's already got a mound. That's, way above groundwater. It's beautiful soil. Why not use that? So what we did is we simply laid the drip tubing, just dig little trenches, laid them all through that whole mound. And now he's got fertilizer, he's got irrigation, he's got a wonderful situation now with that whole system. So it worked out beautifully for him. In fact, this is one of Dervin's projects here. This is Lake Cora. Again, this property here was on Pump and Haul because it was right next to the lake. And it was kind of intriguing. When we did that project, we were looking at it. There was pollution going on out into the lake. And we're going, well, this is Pump and Haul. But it turned out there was a pipe going out of that tank that was going over towards a gutter with a ground stormwater thing. So it really wasn't being pumped and hauled like it should have been. It was effectively a septic tank right by the lake. So what we did there was and the nice thing, again, with drip, you have so much flexibility. You can shape it any way you want. We've done it out in the woods. We had one house in Walloon Lake where the guy had no yard. He just was in the woods. So we just ran it all through the trees. Trees love it. The trees are going to take that water. The key to it is these drip emitters, the roots can't get into them, so they won't clog them. And that's the key to it, and that's why you can do subsurface drip. That one there on Lake Cora, he was almost 15 feet. He was as close to the lake as about 15 feet, but he's getting absolute perfect protection in there. That is not ever going to pollute that lake. It's now, once he gets the grass on there, they're taking the nutrients, they're taking all that stuff. And of course, it's improved the whole performance of the property itself. The property itself is going to have a beautiful lawn, so it's going to be more porous. It's going to be serving that ecological thing much better. And when he did it, his sons were out there working with him, and they got to the end of the project, And they said, is that it? Are we done? I said, what about all the aggregate? What do we do? Where's the stuff? And he's going, no, you're done. And so literally, it is probably the easiest kind of system you can put in. But you have to have clean water. You cannot do it. It does not work with septic effluent. People try to do it with septic effluent. I've seen some of them. You got to be so careful with that because you can get biomat right around the emitter if you don't have clean water, and it'll fail. And I've seen them fail. So the latest one we did, which has been the most fun for us, the Pond Hill Farms up in Harbor Springs is a beautiful area. It's got a brewery, it's a winery, it's got a big farm. They do big events up there all the time. And their big deal every fall is the pumpkin festival. So everybody comes up to buy their pumpkins. Well, 3 years ago, the pumpkins are all in a field about the size of this room. All the kids are out there playing with the pumpkins. They're taking the pumpkins home. Then they discovered their leach field, which was underneath it, had failed and was surfacing. So the Department of Health had to recall all their pumpkins. And of course, the owner of the property is just frantic. It was in the newspapers, on the radio, everything else. So it was probably the worst publicity he's ever gotten. And it was just really, really bad news. So we went, talked to him, said, here, we can recover your leach field, but you really shouldn't have it here, And you're expanding so much, you really need to expand your property anyhow. So what he did is we did it in 2 stages. We started it in this existing system, recovered the leach field. Now that's there as a backup. We then went down below, added more tanks and more treatment, and put in a 3,000 square foot drip field. And he grew this year, or last fall, was the first time he'd been able to use it. So he grew his prize pumpkins there. And there I am sitting with a pumpkin that's well over 500 pounds. He had a pumpkin that was over 1,000 pounds there. We were looking at these pumpkins and we're just going, how do you make a pumpkin that big? And so I told him, I said, well, if you have a lemon, you want to make lemonade. I said, I guess if you have a pumpkin, you might as well make pumpkin pie. So he was very happy. And so he's a very, very happy camper. And that's pretty much what we do.